So now what we're going to do is we're going to investigate the graph of the cosecant theta. We're going to draw the graph of the cosecant theta, right? So the first thing we need to think about is what is the cosecant of theta as a function? The cosecant of theta is equal to 1 divided by the sine of theta. Okay? Now, before we proceed further, so now given this fact, we can see that the graph of the cosecant of theta will somehow be related to the graph of the sine theta. In addition, I want you to notice how this looks kind of similar to 1 over x. See? There's going to be some kind of behavior from 1 over x that we're going to see there, as I suggested, right? Okay. Now, of course, now let's look at, in order to graph the cosecant of theta, I want to begin by graphing the sine theta. And here, we're just going to summarize what we learned before. We know that the sine of theta has some points that are kind of like landmarks, right? So this is at x equals 0, the sine of theta is 0. At x equals pi over 2, or at theta equals pi over 2 rather, because now we're saying theta. At theta equals pi over 2, the sine is 1, right? At theta equals pi, the sine is 0. At theta equals 3 pi over 2, the sine is negative 1. And at theta equals 2 pi, the sine of theta is again 0, right? We saw this when we were graphing the sine, and if you ever forget what these values are, you can always draw a little unit circle on your paper. You can remember that the angles are 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then because this is a unit circle, it has unit radius, and we remember that whenever we think about the unit circle, the sine of theta is the y value of the corresponding point. So here, this point will be 1, 0. This point up here will be 0, 1. This point here will be negative 1, 0. And then finally, this point here will be 0, negative 1. And so consequently, you can see that I read the sine values off of there. See, at angle 0, the y value is 0. At angle pi over 2, the y value is 1, right? At 0, the y value is 0. At pi over 2, the y value is 1. As I continue going this way, at angle pi, the sine value is the y value, which is 0, which is right there. See, crosses at 0. When I go all the way from pi to 3 pi over 2, the y value is negative 1. So you can see that that's why it goes here. And then finally, as we go to 2 pi, the y value goes to 0 again, and so it crosses there. And of course, you can see that if we continue increasing the angle, we continue to go in this direction. And since we went around the circle the first time to draw this piece, when we continue going around, it will duplicate the same graph that way. And if we go toward negative values of theta, we'll go this way. So if we start here and we go 0, negative pi over 2, negative pi, so on, we will duplicate this behavior here, right? Okay. And of course, so right now, so now what I want to do is I want to think, okay, what does that tell us about the cosecant of theta? So first of all, let's look at this value here. If the sine of pi over 2 is 1, and we just saw that it is 1, 1 divided by 1 would be 1. Aha. Right, so we just saw that here at theta equals pi over 2, the sine of theta is 1. So 1 divided by 1 would be 1. So the cosecant of pi over 2 should just be 1. By the same reasoning, we can see that at 3 pi over 2, the sine of 3 pi over 2 is negative 1. So at 3 pi over 2, the cosecant of theta, which would be 1 divided by negative 1, should also be negative 1, right? But now we're going to look at these other values. And these values are special because you can see that this is where the sine is 0, right? So now let's investigate what happens at these values. So for example, let's look at 0. We look at 0 here as I take theta values that go towards 0. See, my sine values are positive. So I end up with 1 divided by a positive number, but a positive number that is getting closer to 0. So just like when we were looking at the 1 over x, if we're dividing by a positive number that's going close to 0, then we're going to get larger and larger values. So we're going to have an asymptote where the cosecant of theta is going to go towards positive infinity. So for example, in other words, the graph of the cosecant of theta. So let me make this sine graph into a dotted line so that we can, I'll tell you why I'm doing this in a second. And so we know that here, the cosecant graph is 1 here, negative 1 here. And what we just made the argument of was that, was that as we go towards theta equals 0, the cosecant theta will asymptote toward positive infinity. Notice that here at pi over 2, as we're coming this way, we can make the same argument. As long as we don't, as we're coming to pi rather, because pi is where the sine of theta is 0. As we come in from this direction, the sine of theta is going to 0, but it's positive. That means we're going to have 1 divided by a value that is positive, but getting smaller and smaller and smaller. So again, as we approach pi over 2, it's going to asymptote like this. It should be more delicate here. Something like that. Let me see if I drew that well. So basically here, as a set of dots, I suggested the vertical asymptote there. Because as we approach pi from the left, the sine of theta is going to 0, but all the sine values there, as long as we're to the left of pi, are positive. And so 1 divided by a positive number will be positive, and as that positive number on the denominator goes to 0, it'll just blow up toward infinity, the values of cosecant theta. Right, so in other words, here there's going to be two behaviors as we're coming from the pi from the left and as we're coming to pi from the right. Okay, we'll get to that in a second. So let's go over here. Here we already know that at 3 pi over 2, the cosecant of theta is negative 1 because we saw that at 3 pi over 2, the sine of theta was negative 1. 1 divided by negative 1 is 1, is negative 1, and so therefore that point is done for us. Now look at what's going to happen as we come towards pi from the positive direction. See here in this region, the sine of theta is negative. So we're going to have 1 divided by a negative number. That's going to be negative. But the sine of theta is going towards 0. So those negative numbers on the bottom, as we come toward pi, are going to become very, very small, but they're going to be negative. So let's say, to connect it with our previous, to think about it in more practical terms, let's say negative 110, negative 1 over 100, negative 1 over 1 over a million. 1 over those numbers gets progressively larger, but larger negative. So in other words, here, this is going to asymptote downwards like this, right? And by the same reasoning, we can see that at 2 pi, let me try and draw this asymptote for us. Right, because as we go towards 2 pi from the left, the sine of theta goes to 0, but the sine of theta is negative in that region. And so we're going to have 1 divided by a negative number, which will give us a negative result. And that negative number is going to go to 0. So that means it's going to be getting increasingly large negative. And what I'm going to do now is I'm going to erase now the graph of the sine from what we from our graph of our cosecant. Okay. Okay. Perfect. And this reveals for us the graph of the cosecant of theta. And of course, we know that the sine theta that was here before repeats that pattern, as we go this way and as we go this way. So the graph would also continue. So for example, over here, there would be another piece that looks like this. There would be and then there's an asymptote, and there's a piece that looks like this. And then likewise over here, right, there's a piece. Well, this should be smoother, right? Like this. And then like this, right? And of course, we know that in this case, right, we know that this is 2 pi. So right here at where the cosecant of theta value is 1 again, it's 2 pi plus pi and a half. So that would be, let me see, 2 pi is 4 pi over 2. So that would be 5 pi over 2 right here in the theta. Here, it would be at 3 pi. Here, it would be at 7 pi over 2. Here, it would be at 8 pi over 2. And similarly, going backwards, right, 0, this will be negative pi over 2. And you can see that here, right? If we go here, that's negative pi over 2. And it makes sense, therefore, that the value of the cosecant theta is negative 1. Because if we start at 0 and we go to negative values of theta, remember, when we go to the left, we're going negative values of theta on the unit circle. So as we go negative pi over 2, our sine theta is negative 1. And when we plug that in here, 1 over negative 1 is negative 1. So that makes perfect sense. And so there you have it. And let me see. Any other comments I want to make here at this moment? Hmm. 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 Before we talk about the other functions, I just want to show you, we graphed the cosecant of theta on one period concretely, and we hinted at, we more than hinted, but you can see that the pattern continues, right? But what I want to point out before we close this video is that we can take all our knowledge about how to graph sine functions, right? More complicated sine functions, to graph more complicated cosecant examples. Because we will first, what we'll tend to do is, well, the way I'm going to suggest you to do it is first you're going to draw the sine graph, and then, for example, very lightly with very light pencil, and then you can erase it, just like we did here. And so now, speaking more broadly, when we're going to graph examples of the cosecant of theta, what we're going to do is we're going to use either the points method or the other technique, the systematic technique, either of those methods, to graph the sine theta. The sine, whatever sine function we get, or sine of open parentheses theta plus pi over 2 close parentheses minus 3, or whatever the sine function is. We're going to graph it very delicately, very lightly with pencil, knowing that we're going to erase it when we graph the cosecant part. Just like here, I graphed my sine, I used it to draw my cosecant, and then I erased it, okay? And of course, we represent our asymptotes very delicately with dotted lines, so that we remind ourselves that those are asymptotes, okay? In any case, I hope you've enjoyed this example, and thank you. You're still there? You're watching this video? Well, I hope you enjoyed it. In any case, if you did enjoy it, well, I encourage you to like it. Put that big thumbs up there. And don't hesitate, and don't forget to subscribe to my channel. And anyway, and also add a comment if you want me to cover some particular topic. I can't make any promises. There's a huge list of topics I already want to cover, but time permitting, I may address that topic. And in any case, I hope you've enjoyed this video, and thank you again.